So again, the purpose of today is kind of twofold. The first is to understand how to compute an expected value. So that's the big math topic that is wrapped up today. Compute an expected value. But more than just the computation, what I like about quantitative reasoning-oriented classes is that we care as much about what those computations mean and what we can do with that information as we do how to actually get the computations. So the real goal that you would be interested in if you're thinking about the processes of gambling is to figure out how to decide.
Are you the guy from YouTube?
I am a guy from YouTube.
Oh,
There are a lot of guys on YouTube, but yes, I'm one of them. How to decide whether a wager is worth taking. Yeah, we're kind of married. I wouldn't say famous. I wouldn't say famous. So here's the opening discussion question for today. The question is it worth it, and you get to decide what that means, to buy a lottery ticket for Powerball? Is it worth it to you? So take one or two other people and come up with at least one reason why the answer to that question might be yes, it is worth it to buy a Powerball ticket, and also at least one reason why the answer to that question might be no. So take 2 or 3 minutes, talk to the people around you, come up with one reason for both yes and no. All right, so I'm going to start by asking this side of the room, somebody from this side of the room, to give me an answer to either yes or no. Why is it to you either worth it or not worth it to buy a Powerball ticket?
I guess it's kind of worth it because it's only $2.
Okay, right. So we have here a reason why it might be worth it is because a ticket for Powerball is not that expensive, right? How much are you actually risking to go buy one ticket for Powerball? Yeah. Yes, because you're only risking $2. Which, depending on your current financial situation, may or may not feel like a lot of money. But let's tentatively kind of agree that at least in comparison to the amount that you could win, $2 is not really all that much. So that might be one reason why it would be worth it. Yeah.
I'd say, math-wise, technically, I don't think it's worth it.
Okay, because?
You can take that $2, and I was just explaining, then you take $2 and buy pick 3 or pick 4, you know what I mean? Like, you know what I mean?
Okay, and
Hitting a pick 3 or pick 4, great.
why might that be a better investment than Powerball to do pick 3 or pick 4?
It's the options, the amount of options you have with the balls and whatever.
Okay.
I know they're greater than hitting 6 random numbers, 1 through what? 1 through 50? 1 through 60?
Right, I think there's 50 options for the Powerball, the red ball itself, and I think there's 60 for the white balls, yeah.
So, realistically, it's nearly impossible.
Nearly impossible. Finish that sentence for me.
Nearly impossible to get them all.
Okay, so it's nearly impossible, or let's say very improbable, to hit the jackpot. Right?
But people do.
It happens. I mean, it makes the news when it does, right? Especially when the jackpots get really, really large. Like there was a jackpot recently that approached almost $1 billion. It was ridiculous. And then I think how many people actually ended up splitting that jackpot? There were 3 winners.
One of them, the guys that he's already
Yeah, where's the justice, right? So we have a couple of reasons up here that it's not a good idea. Maybe we could take that $2 and go in and find a different lottery ticket or a different, gambling product that might have better odds of winning. Because for Powerball, it's very difficult to hit that jackpot because you have to get all 5 of the white balls right and you have to get the red Powerball right in order to get that $101 million. Did anyone come up with other reasons why it might be worth it to buy a Powerball ticket?
$2 into $1 million.
Yeah, right. So that's the upside, right? And this is the reason I think people do play Powerball is that it's $2 and you could turn that $2 into a whole lot of money, $101 million in the current jackpot. So how do we then make a decision about whether or not when I leave class today I should go over to the gas station and get myself a Powerball ticket? We need to somehow balance all of the information that's up here. And the two probably let's say 3 most important pieces of information up here are, first of all, the amount that we're risking by buying a lottery ticket. So this is our exposure. In a way, this limits our loss. if I only spend $2 on a lottery ticket, then the worst thing that could happen is I lose that $2 and I don't win anything. So the first piece of information is the amount of risk. The second is the amount of potential reward. There are a lot of different ways that Powerball can pay out, but for the sake of this argument, let's be simple and let's just focus on the jackpot. Let's imagine the other prizes don't exist. So we have to somehow incorporate a balance between that risk and that possible profit from winning this wager. But what's the third most and probably most important element on here for your decision? Besides the risk and the possible reward, what else is most important to our decision on this list? Maybe under the no column. Yeah, it's not even that high, right? It's a minuscule chance that you're actually going to hit that jackpot. So there's two kinds of information that we need in order to make this decision, make a decision whether or not a wager, which is really what buying a Powerball ticket is, it's a wager that you're going to win the jackpot. We need to know the amounts of risk and potential reward. Risk and reward. And these come in dollars, usually. But then we also need to know what is the probability. How likely is it that we're actually going to win? In the case of Powerball, the odds of winning the jackpot are 1 in, oh gosh. Powerball publishes these statistics, these odds. You can find them on the Powerball official website. It's a many million to 1 shot to win the Powerball. So it's a very, very small probability. It's not 1%, it's not a tenth of 1%. It's on the order of 100,000th of 1% to actually win the jackpot in Powerball. And even if you did win the jackpot, there's a chance that other people also did, and you're going to have to split that money, which also affects your decision because it changes the amount of your reward. Right? So we need a mathematical way to balance these two forces. The risk and reward, and because the reward is so high, it pulls us towards wanting to buy a Powerball ticket, balanced by the probability of winning, which is so low that it pulls us toward not wanting to buy a Powerball ticket. So how do we balance those two forces against one another? Powerball is kind of complicated just because the odds are so long and the payouts are so large. Let's choose a smaller example to play with. Instead of Powerball, let's just imagine a simple experiment where I flip a coin, a fair coin, and I just flip it once. So the only possibilities for that coin is it might come up heads or it might come up tails. And of course, we want to make this coin flip interesting. So we place some, we're going to place some wagers on it. But first of all, let me ask you this. If I'm flipping a fair coin, then what is the probability that that coin is going to come up heads? 50-50. So as a number, if we wanted to quantify that, what number could we use to quantify a 50-50 shot? What is the probability? What would we say? As a number. What percentage of the time, let me put it this way, what percentage of the time would we expect a coin to come up heads? 50%. That's what you mean by a 50-50 shot. So we'll say that the probability of heads is 50%, or as a decimal we can write that as 0.5. So that's the probability this coin comes up heads. 0.5 is also the probability that this coin comes up tails. That's the other 50 in the 50-50, right? So if it is a fair coin, then these are the probabilities that the coin will come up heads or tails. 0.5, 50% for each. So if we make it interesting by giving each one of these different outcomes a dollar value that you can win, then we can ask the question, is it worth it to play this game? Right? Do I expect to come out ahead, or do I not expect to come out ahead? So let's suppose that we set the payout structure as shown here. If the coin comes up heads, then you win $1. If the coin doesn't, if it comes up tails, you win nothing. So that's how the game, the payouts work. You can kind of imagine that heads is like winning the Powerball, tails is not winning the Powerball, in a way. Now let's assume that this game costs you absolutely nothing. It's free to play. Is it worth it?
Oh, yeah.
Yeah, why?
There's no risk.
There's absolutely no risk. If it costs you nothing, then the worst thing that could happen is the coin comes up tails and you don't win anything, but then you haven't lost anything either. You haven't exposed yourself to any risk because there's no cost to playing this game. The best thing that could happen is the coin comes up heads, you walk away with an extra $1. So I think this is absolutely worth it to play if there's no cost whatsoever. So of course the interesting thing is let's change the cost to play and ask that question again. What if the game costs you $1 to play? You're shaking your head. Why? Why is it not worth it to play if it costs you $1?
Because if you lose, like, you don't win that much, but you don't lose that much.
Right, so if we lose, then we're out $1. If we win, and I suppose I should have been a little clear on what I mean by these payouts. If I win, then I get my $1 back, basically. So I pay in $1 to play this game, and if I win, I get that $1 back. So what's the best thing that could happen? You break even, right? So the best possible outcome is we break even and walk away with no profit. The worst thing that could happen is we lose our $1. So clearly here, the risk outweighs the reward. And so this is not a good idea to play. So it's an easy question to answer if the game is free or if the game costs us $1. So what about the costs in between? Let's say it costs me $0.25 to play. Now what?
Worth it a little more.
Okay, so we're in this middle ground. I saw some heads nodding here. So who thinks that this game is worth playing at $0.25? And who would not play this game if it cost $0.25? Well, looks like everybody with an opinion is saying that yes, this gamble is worth it. So why is $0.25 worth it when $1 wasn't? You could triple your profit. Sure, you could, right? Because if I win, I get back $1, which gives me 75 cents more than I wagered, right? Which is 3 times as much as my initial wager. So I could triple my profit. But I could also lose that quarter. So what about that? Right? There is a risk involved this time. Why is that risk not big enough to persuade us not to play?
Because it's only a quarter, it's not that much.
Okay, it's only $0.25, and in comparison to the $1 that we could win, it's not that much. Let me ask you this. Are your decisions taking into account the probability of coming up heads or tails? How does that 50-50 shot figure into your decision?
You flip the coin 10 times and you come up tails like 9 times.
Ooh, there's an interesting point. So if you flip a coin 10 times, can you say the rest of what you just said?
I said if you flip a coin 10 times, 10 times, 9 times, you beat tails.
If you flip a coin 10 times, 9 times comes up tails. If that happened, what would you expect? What would you suspect about that coin? Yeah, something's fishy with the coin if it comes up tails 9 times out of 10. Well, you might suspect that. There's a small probability that that might happen anyway, even with a fair coin. But chances are, and chances are is what today is all about. Chances are, if I flip a coin 10 times, what's going to happen?
You're going to get it 5 times tails, 5 times heads.
That's exactly what we're trying to quantify today, right? That what we would expect to happen on the average if I flipped a coin 10 times is that 5 times that coin would come up heads and 5 times that coin will come up tails. That's what would happen if we flipped the coin a whole lot of times. Right? On average, we expect it to come up tails half the time and come up heads half the time because those are the probabilities of heads and tails. So if I flipped a coin in this game 10 times, let's figure out what we would expect to happen. 5 times, I would end up with heads. Each time I had heads, how much would I win? $1. So how much would my profits be from these 5 heads? $5 of winnings. But then the other 5 times when the coin came up tails, what would happen? I get nothing. Right? So I win nothing. And how much would it cost me to play this game 10 times?
$250.
Yeah. So the cost for 10 plays is $250. And so if I went to some fictional casino that has this game going, which is probably not a casino that makes much money, but if I went to a casino that was doing this and I paid $250 to have 10 shots at this game, then what I would expect to happen is that I would win 5 of those games. I would walk away with $5 having only paid $250 to play. So, is this a smart gamble? I think it is, right? We expect to walk away with more than we have to pay to play. So costing 25 cents per game makes this a smart wager. What about 75 cents a game? See, because you've got 75 cents of risk, but you could still make a profit of $1, right? Well, not a profit of $1, a profit of 25 cents if you come up heads. But you're shaking your head now. Why? Why is this no longer a good idea?
Because if you flip it 10 times, then you'd have to pay
So you'd end up paying $7.50 for those 10 tries at this game. And what would you expect would be the outcome? Right. So if the on average thing happens, then you get 5 wins and 5 losses, and those 5 wins are going to get you $5 back from the house. But you had to pay $7.50 to get that $5 back from the house. It's a $1 a win, right? So you end up getting $5 back having paid $7.50 in, and that sounds like a bad investment. If what happens on average ends up happening to you, you will walk away with less money than you started the game with. So that's a bad investment. So my question, and this is the big question of the day, is where is the tipping point? How much, if we set the game as costing that much, would it be a toss-up whether you should play or not? 25 cents, bad investment, or good investment. 75 cents, bad investment. Free, great investment. $1 to play, terrible investment. Where's the balance? Where's the point right in the middle? 50. 50 cents a game. If this game cost me 50 cents to play, then is it worth it to play? No, yes, both, neither. Yeah, so that's the reason I put unsure as one of the options up here. So 50 cents is the unique, interesting place to set the cost of this game. Because if what happens on average happens in a series of 10 plays, how much do those 10 plays cost us in total? $5. So the 10 plays cost us $5, and on average, we expect 5 wins and 5 losses. 5 losses are going to get me nothing back from the house, but 5 wins are going to get me a total of $5 back from the house. So on average, I expect that exactly what I pay to play is going to come back to me from the house, and I'm going to walk away having broken even. Right? And anytime we expect to break even in a game, that makes it a toss-up, whether we decide to play the game or not. We might feel lucky, right? Which is kind of what powers most gambling, and believe that we're not going to come away with 5 wins and 5 losses. We would come away with 6 wins and 4 losses, right? Which can happen, in flipping a coin 10 times. And in that case, we would make a profit. But there's just as much chance that we would have fewer wins than we have losses and end up losing money over 10 plays. So 50 cents is a balance point. And that balance point is what finding the expected value is all about. So here's what powers this example. What we know about this game is that we know how much money we would win with each of the possible outcomes, either heads or tails. And we also know the likelihood, the probability of each of those outcomes. The coin comes up heads with a probability of 0.5, 50%. And the coin comes up tails with a probability of 0.5, also 50%. And we know that in each of those outcomes, there's a certain amount of winnings. If the outcome is heads, then the amount of winnings is $1. If the outcome is tails, then the amount of winnings is nothing. So, in order to balance these two forces, the amount that we could win with the likelihood of each outcome, what we want is, again, to ask the question that you've already sort of led us to, which is what happens on average in this game? If I play this game only once, then I either win $0 or I win $1. Those are the only possible outcomes. If I play the game twice, I could walk away with $2, right, if I won both times. I could walk away with nothing if I lost both times, or I could walk away with $1 if I won once and lost once. And on a per game basis, if we divide those by 2, then either I can expect to win nothing per game, $1 per game if we win them both, or an average of 50 cents per game if I won one and lost one. Right? So this is kind of the key, is looking at it on a per game basis. If I play twice, these are the possible amounts I could win per game, dividing the total by the number of games that we played. Amp that up to 4 times, and there are 5 different possibilities. I could win $0 if I lost all 4 times. I could win $4 if I won all 4 games, or I could win any amount in between. Right? I could win $3 by winning 3 times and losing once. Right? And on a per game basis, if I divide these numbers by 4, that means that I could win any one of these amounts per game over the course of 4 games. Right? I could win anything from $0 to $1 and any number of quarters in between on a per game basis over 4 games. If I play 1,000 games, and I'm not going to list out all those possibilities, possibilities. But if I play 1,000 games, I expect to win 500 of them. How do I know that? Why would I expect to win 500 times over 1,000 games? Right, because it's half. I expect to win half of the time because the probability of winning is 1/2. So I would expect if I played this game over and over and over again, I kept coming back to the casino, the terrible casino, it's probably not making a profit. If I kept coming back to it, I would win half the time. If I win 500 games, then I make $500. And on a per game basis, dividing that by 1,000, what do I get? 50 cents per game. So that 50 cents is really important. It tells us, on average, if we were to do this over and over and over and over and over and over again, 1,000 times, 1,000,000 times, 1,000,000,000 times, it tells us how much per game we would expect to come away with. So on average, this game is only worth playing if we can expect to walk away with more than we had to pay. Right? So it's only worth playing this game if it's going to cost us less than 50 cents to play, because we're only expecting to win per game 50 cents. So that 50 cents is really important. And what we call that 50 cents is we call it the expected value of our profit. So this is where we're getting to for the whole first 20 minutes of today. Is that the expected value is defined to be the average value that a quantity, or a random quantity, takes over a large series of repeated trials. So I play the game 1,000 times repeatedly, and the average amount that I win over those 1,000 times is an approximation of the expected value. So how do we compute such a thing? We can compute it by taking what is in essence a weighted average. So weighted average is the mathematical power behind all of this. In a weighted average, we are averaging the possible amounts of winnings weighted by the probability of those winnings actually happening. So according to the sort of the formula that I've written down here, what you end up doing is taking the amount of winnings for each of the possible outcomes and multiplying that amount by the probability of that actually happening. So for the outcome heads, which pays out $1 and which happens with a probability of 0.5, I'll multiply $1 by 0.5 and get 50 cents, $0.5. And that gives me the contribution to the expected value of my winnings that comes from the number of times that I win. But we can't stop there because we also have to balance that out with the contribution from the times that I lose. I lose, I get a tails, with a probability of 0.5, and every time that happens, my winnings are 0. So I'll multiply those quantities together as well. What's 0 times 0.5? 0, yeah, 0 times anything, right? Okay, so we take each of the winning amounts and the probabilities and we multiply those across to get the contributions to the expected value. And now we've taken all in this formula, the products, x, the amount, times p of x, the probability of getting that amount. But then what do we do with those numbers afterwards according to this formula? What's that key word in there telling us to do? Add, exactly. So that's all we'll do to finish the expected value calculation is we'll just add 50 cents to 0 cents, and we'll get, that's not too challenging of an addition problem, 50 cents. That is my expected value, which also happened to be the maximum amount that we would be willing to pay in order to play this silly coin flipping game, right? The expected value of my winnings was 50 cents. So if it's going to cost me any more than 50 cents to play this game, then I'm not going to walk away with a profit on average. I don't expect to walk away with a profit. But if it costs me less than 50 cents to play, then on average I will walk away better than when I came. And that quantity, which results from multiplying the amounts by their probabilities and then adding all those results, is called the expected value of that random quantity.